Hello and welcome to our notes on Newton's third law. This is the last of Newton's famous three laws of motion. The first law, if you remember, was an object that is either in motion or at rest stays that way unless acted upon by an outside net force. So essentially what this means is objects will continue to do whatever they are currently doing unless a net force is acting upon them. Then they will change what they are doing. They might go from being in motion to being at rest. They might go from being at rest to being in motion. They might go from being in motion to being in a different type of motion, speeding up, slowing down, changing direction. But the object will not do that. Nothing will change unless there is a net force acting on it. So if there's no net force, the object will continue to do whatever it's doing with no changes. Newton's second law is really just a restatement of the first law, but in equation form, with slightly different terms. Newton's second law is F net equals ma. This is Newton's second law. It says that the net force on an object is equal to its mass multiplied by its acceleration. And we've been writing F net statements ever since we learned about that. Newton's third law is just as simple as these, but I think it's probably one of the more misunderstood parts of physics. Newton's third law is for every action, I'm going to leave something in parentheses there for a sec, there is an equal and opposite reaction. And I'll put something in parentheses there as well. For every action, there's an equal and opposite reaction. One of the reasons I don't think this is very clear to students is because it's not really clear what action and reaction mean. What Newton is talking about here is forces. For every action or force, there's an equal and opposite reaction, another force. Okay, not a reforce, but another force. The key here is that forces always act in pairs. Okay, we will start to talk about force pairs when we talk about Newton's third law. Now, what you're thinking is, oh yeah, that makes sense. On a free body diagram, if there's an up force, there's almost always usually a down force. That is not what we are talking about here. This is not the same as a free body diagram in which two forces act in opposite directions, such as Fn and Fg often do. Not the same thing. Let me give an example of a Newton's third law force pair. You push against a box with an applied force. Okay, you are applying a force to the box, the force is coming from you. What is the equal and opposite force in the Newton's third law force pair? If you are pushing on the box, then we would say that the box is also pushing back on you. It is also exerting a force on you. The box pushes back on you with an applied force. So while you push on the box also pushes back on you. Okay? Now, you might say, well, how is the box pushing on me? Well, you're exerting a force on the box, you're in contact with the box. We could say either you're in contact with the box or the box is in contact with you. It makes no difference, okay? What someone who doesn't know what they're talking about might say is that the equal and opposite force is the force of friction. That's not true, okay? The equal and opposite force is not the force of friction. And let's explain why. It's not because those two forces can exist without each other. And by those two forces, we're talking about the force of friction and the applied force. They can exist without each other. Let's imagine that you had this box on a frictionless surface. If that was the case, you could push on this box, you can have an applied force, Fa, with no force of friction. That's your first clue that this is not a Newton's third law force pair, the applied force and the force of friction, even though they point in opposite directions. You could have an applied force without a force of friction. Or imagine you have an object that was pushed away and is coming to rest. An object that you pushed away and that is now coming to rest might have the force of friction on it, but it would not have any applied force on it. It would have the force of friction, not the applied force. Okay? So again, when we're talking about Newton's third law of force pairs, it's forces that are exerted between two objects that are interacting. So I gave the example of you push against a box, the box also pushes back on you. The size of the forces is the same, the direction is different, or direction is exactly opposite. There's no way that you can put a force on the box that the box does not put a force back on you. Now, why does the box move and you don't? We're going to get into talking about that a little bit later. Let me give you another example. Hopefully you can see this one. I have two spring scales here. This one is rated for 2.5 newtons. And this is not going to be very easy to see, I can tell that right now, but we'll do it anyways. This spring scale is rated for 5 newtons, okay? If I pull on the spring scales, we can see, okay, you can't really see. Okay, actually, here we go. So you can see that the blue one is at 2.5 newtons. Without changing anything else, we can see that the green one is at 2.5 newtons as well. As a matter of fact, if I don't pull as hard, you can see both of their meters go back up. That's at 1.5, and this one is just about at 1.5. So we're seeing that these two springs are exerting the same amount of force on each other. Okay, another example of Newton's third law. You can do that with spring scales. You can do it with actual like bathroom scales. You can put them back to back and have two people push on them, and they'll always read the same thing. You can do it with a lot of different things. Let's do another example. You're standing on the ground. Your feet are exerting a force as they push down on the ground. What is the equal and opposite force? Okay, so your feet are pushing the ground. Well, guess what the equal and opposite force is? It is the ground, or maybe the force of the ground, let's say that. Pushing up on your feet. Okay? Your feet are pushing down on the ground. The ground pushes up on your feet. You can't have one without the other. Your feet can't push on the ground without the ground pushing back. That's how Newton's third law works. So notice really all we're doing is we're changing the order of the objects that we're talking about. Force of feet on ground equals force of ground on feet. Those are just in opposite directions. Last example on this page, let's say you're standing on the ground and you're being pulled down due to the force of gravity on you from the earth. What is the equal and opposite force? Now, sometimes people will get confused here and they'll say, it must be the normal force, the force upwards from the ground. But that's not really what this is going on here. If the earth is putting a force on you through the force of gravity, then guess what? The equal and opposite force in this case is the force of gravity you exert on the earth. You actually exert a force of gravity on the earth, okay? The earth pulls on you, you must be pulling back on the earth as well. Now, that means that if you jump upwards, okay, and you separate yourself a little bit from earth, guess what? You are pulling earth towards you at that time. Kind of crazy, right? Sounds like I'm lying. I'm not. You actually pull the earth towards you just as the earth pulls you. Or you pull the earth towards you just as you are pulled towards the earth by the earth. Okay? Newton's third law says that you each exert equal forces on that you and the earth exert equal forces on the other object. The directions of those forces are just different. Now, the obvious reason, why don't I see the earth accelerate towards me? Think about the size of the earth. The earth is huge. Okay? Your mass is very small compared to the earth's. Your force on the earth is not going to cause that huge object to accelerate towards you at any noticeable rate. But it does. It does accelerate towards you just a little bit if you were to jump off the ground, okay? You are pulling the earth towards you. You have to accept that fact if you're accepting Newton's third law. I know it sounds weird, but it is absolutely true. Oh, hopefully you got that last line. Let me put that back up there for a second. Okay. A couple more examples and then we're done. Newton's third law is very short. It's confusing because it sounds almost made up, but it is 100% verifiable in fact. Example, a 10 Newton golf club hits a 0.45 Newton golf ball. By the way, those are the weights of the objects. Remember, if we have a number listed in newtons and then an object, that's telling us about the weight. Hits a 0.45 Newton golf ball forward with a force of 10,000 newtons. And that's not a weight, that is a force where the club is putting on the ball. What is the magnitude and direction of the force on the golf club from the golf ball? So we're saying the club puts a force on the ball of 10,000 newtons. What force does the ball put back on the club? Newton's third law tells us it must be the same force that's exerted on the ball by the club, but it's just backwards. It's in the opposite direction. From ball to club. Now, this can be confusing to people. Okay? If that force is so big on the club, how come the club doesn't go flying as far as the golf ball? There's two reasons I can think of. The first is the club has more mass. And one thing that we learned when we talked about Newton's second law is that objects with more mass do not accelerate as easily. Doesn't accelerate as much. The other reason is that the golf ball is kind of isolated. There's no other forces to hold back the golf ball. The club, however, has other forces acting on it. Like your hands, for instance. The ball doesn't have those steadying forces while the club does. Okay? That's why the ball can go flying upwards of 200 yards while the club stays in your hands and continues on its swing relatively without any change. So our conclusion that we're reaching. When we talk about Newton's third law of force pairs, it is important to remember that we're not talking about forces that just point in opposite directions on a free body diagram. That is never going to be a force pair. It is the idea that two objects that are interacting via a force, object A will put a force on object B, and object B will put the same force, the exact same magnitude, right back on object A. The only difference is in their direction. Their directions are exactly opposite. So Newton's third law of force pairs are always equal. Whether or not something moves depends on its mass and other forces acting on it. So if we go back to our first example, you push on a box. What's the Newton's third law of force pair? The box pushes back on you. The reason that you are able to move the box and the box doesn't move you backwards is because you have other forces holding you in place, notably friction. The box's friction holding it in place too, but you must be able to overcome that friction. The box's force does not overcome that friction that keeps you in place. Also, you probably have more mass than the box, so you're just harder to accelerate anyways. One last example, using force pairs, explain how we're able to walk forward. Okay? How are we able to walk? Think about the forces that you exert when you walk. When you go to take a step, what you're doing is you push downward and backward on the ground. So you are pushing downward and backward on the ground. What direction do you think the ground pushes you? Ground pushes up and forward on us. If you're talking about you and the ground, you have less mass than the ground and you don't have other things holding you in place. So we accelerate. The ground, on the other hand, mostly stays in place. There is a tiny effect, but it's not something that's measurable, okay? When we say it's not measurable, we just can't, there's no way we can measure it. It's so imperceptibly small. But Newton's third law says that that effect is there, okay? So that's how we walk forward. Push down and backwards on the ground. Ground pushes up and forwards on us because of Newton's third law. Our force of pushing on the ground is the same as the ground's force of pushing back on us. They're in opposite directions, but they must have the same magnitude. We move forward because we have less mass and we don't have other forces fixing us in place. The ground is all kind of attached to different parts of the ground that can't move quite as easily. That's Newton's third law in a nutshell. It is fairly easy once you get the hang of it, but it sounds very strange, okay? I believe our next set of videos will be on the spring force, and then actually, we're almost done with the forces unit. After the spring force, we just have one more topic to talk about, okay? It is a bit of a challenging topic, but we'll get there in a little bit. As always, if you have any questions, let me know, and I'll talk to you soon.